Hello. So we will continue with the sixth lecture. Last time we ended with the concept of matrices and operations of matrices. Today we will have invertible maps, invertibility, linear maps, isomorphism, and then we will discuss some motion of matrix multiplications, linear maps as matrix uh, multiplication, and then we will go linear operators. So let's start by defining an invertible map. So this map, the um, V to double is invertible if exists a map, there is a linear map S in W, uh, LW to V, the interchange of the main and domain node, that scenario here, such that your S times T here is the identity of V, and T times S is the identity of W. And then um, the map, a linear map S is uh, the inverse our. Okay. So let's have a theorem. So inverse is unique. So I will not prove this. This is just the same as the proof on uniqueness of inverse function. And then notation for E from B W, its inverse, we denote its inverse, inverse. All right. Now we have this common result. This is actually the same with what you have in the properties of functions, but we add an extra property, which is the homogeneity. This, this is the same. So invertibility, invertibility uh, is equivalent to injectivity, or being on, and emphasize and subjectivity. Sabihin, subjectivity must be surjective and injective. Then we we have an invertible linear map. So the proof of this theorem is common, and this is the same with the functions from your previous courses. But we had an extra assumption on homogeneity. Now we go to some examples of linear maps which are not ordered. We know that if we have x squared multiplication by x squared is a linear map from the polynomials with coefficients of r, polynomials with coefficients of r. is not inverted because it one is not in range. It's the power of all the powers in the x in the codomain in the range starts with x to the second degree or x squared. And then the other one is backward shift. So we have map from f infinity. Where is we have here in the I, then the one here in the I takes this b acts by transferring one in the I I plus one I plus I plus okay, that's it. Non-invertible linear maps. Now, because we have the concept of inverse, we'll consider small ice vector spaces. Let us define what's an isomorphism first. An isomorphism is an invertible linear map. Uh, if V and W are vector spaces, and we have I here, we say that V and isomorph V is isomorph. We can think of them as isomorphism as we have before is just thinking as elements labeling label V in V by POV in. And then we have a special group here that is important. If we have two vector spaces over F, they are isomorphic if and only if a dimension W is the dimension. This is the invariant dimension. The two vector spaces which are isomorphic have the same dimension. So I think we need to prove this. Let us start the proof. One, go with the direction suppose that E and W are isomorphic. Then First, here we will only consider VW as VW finite dimensional, because we have uh, noted earlier that all vector spaces that we will use in our theorems are mostly assumed to be finite dimensional unless stated. So because they're isomorphic, you can have map T from V to W, which is isomorphism. And then after that, since this is an isomorphism, the range of T is equal to W, and then the null space of our T is just the zero vector. This means that the dimension of range of T is equal to dimension of W. Then now that the formula thing V is equal to range, dimension of the range was the dimension of the null space of T. Kernel is our first uh first fundamental theorem of linear map, and we know this is of dimension. This one here, dimension is zero. Thus we get the dimension of our is equal to the dimension of our that's the first part. Uh, Now the second part is V and W are isomorphic. Saying that V and W are of the same dimension. Okay. Suppose the dimension of V is equal to the dimension of W. Let us consider V1, Vn, the basis of V, and W1, Wn, basis of our W. And then take map D from V to W is defined as follows. This is just is a linear combination elements bases in the vector space C1 plus N2. This is well defined. Is well defined because since V1 to Vn is basis of T. Now T spans W since one W1 and is linearly independent and is of course the basis, and means that T spans okay, let me rephrase this one. Say that T is surjective since the null space of T is just zero since W1 are linearly independent Is we can just get zero by just plugging the constants to be of zero. In this case, we have already the subjectivity S, and then here E is objective since the null space is zero. That means we have surjectivity and ejectivity. We have is an isomorphism. Okay. That's it. So from the previous result, um, what can you say? Here, here, every finite dimensional vector space is isomorphic, and where the dimension V. We have another important theorem that I will here follows from this one. This is the following. The linear map from V to W is isomorphic. When I say isomorphic, here we have vector space. Our matrix of M by per our field. This is the name of the F M. The proof is just uh, from three from uh, and of course because the dimension of FMN is just this is a corollary for this is the dimension of linear map from V to W is equal to the dimension of V times the dimension of the whole. Right. What we get. So because of that, we have defined matrix of the linear map. So we define the matrix of vector, and then we can think of linear maps as matrix multiplication. So linear map plus matrix. So we first define matrix vector MOV matrix vector V the main vector space. Then consider V1 to be a basis. This like say basis, something I just mean this B1 element of the basis. Sometimes I say for the base B1, what I really mean is for B1 an element of the basis V, basis of vector space V. Then this matrix then is C1, Cn, where of course C1, C's, I's are in F, and your V is linear combination of the bases C1, V1. Cn, Dn. As an example, let us look at the following. We have following standard basis. With respect to standard basis, 1, 0, 0, 0, 1, 0, and 0, 0, 1, are, let's say, F3. Here, let's consider FR, the matrix. The basis of E R D standard basis are 3, so you have 1 x squared, and then x raised to 3 is basis are standard basis. And the vector, the vector here is a polynomial, an element of this vector space. In the element, let's consider is V, is 2 minus 7x plus 5x. We can think of this as 2, negative 7, and then third component here will be like the matrix or matrix, the vector. Matrix representation. So with respect to standard basis, of our f to the n, we get the vector element of f to the n is just x1, x, xn, where of course there is one x1 only 1, xn. But here xi's are our field. Another position is the following. Suppose E is an element of the linear map from V to W. We have standard well basis of 1 to n, basis and then the W1, n basis of here is m, this is n, and then kb from 1 to n. The k column matrix, the linear map of T. And the M, we have T here, and we have that. K is just the equal to the matrix of the vector is K, where K here is what? It's the K base, K component of the basis of V. So now we can think of linear map acting as matrix multiplication. Here, the same assumption, V to W, and of course we have T here, element of V. Then V1, Vn, 1, M, basis, basis, U. Then, then we get this matrix of the linear map. Linear, a linear map if applied to the vector V, which is equal to the matrix of the linear map T times the matrix of the vector V. I think this is important. It somehow show the proof. Suppose that our vector V is C1, V1, Cn, V. This is an element. Of course, your CIs are F, F, your D of V is just C1, D of V1, Cn, D of Vn. And then the matrix of map TV is equal to C1, and then matrix of TV1 plus Cn matrix of TVn. And you know, this is just C1 matrix of T, and then this is 1, and then Cn matrix of T, and then the n. So the column, the n column of the matrix of T is just matrix of T multiplied by the matrix vector V. So this comes from this idea here. And we use this idea to show that the matrix of the linear map of the linear transformation applied to the vector is just equal to multiplying the matrix of T, the linear map, times the matrix of the vector V as defined here. Here, of the matrix vector V. That's it. Let me say some remark here. H M by N matrix produces a map from N1 to M1, namely the result of matrix multiplication. It takes X in F n comma 1 to AX in F raised to M. You can think of linear map as matrix multiplication after suitable labeling by isomorphism given by matrix. In this book, uh, we will consider linear maps abstractly, and we will consider linear maps more than matrices. However, sometimes it's thinking of linear maps as matrices or thinking of matrices as linear maps, vice versa, gives important insight. And so we will be interchanging in both worlds. Most of the concepts, most of the presentations here will be in language linear maps. Now we have some special kinds of linear maps. A linear map of vector to itself, and we call them operators. So what are operators? Let's define operators. This is just the linear map. A linear map from itself is an operator. An operator. And then next one is L of V. It's just that operators. on the, so this is just what L V. So most of the theorems in the algebra, which are very deep and elegant, deals with operators. As you can browse the content of the book, we have special operators, there are product spaces, operators in real vector spaces, operators in complex vector spaces. Map is invertible if it is injective and surjective, as we have stated earlier. And for an operator, you might wonder uh, whether injectivity or surjectivity alone is enough to imply invertibility. So let us uh, give an example which says that neither injectivity nor surjectivity implies invertibility. But the definitions, some example is saying the fact that neither injectivity nor surjectivity imply invertibility. Again, we have earlier x squared, an operator of the polynomial over R is injective. Then the next example is backward shift, which is already stated earlier on is surjective, but not injective. So that we go back to, so kindly check these examples at home. And yeah, let us consider equivalence, injectivity, and surjectivity for finite dimensions. Uh, Note that for backward shift, it is subjective but not injective. Check this. F to infinity is the finite dimensional vector space. Uh, Verify this. Now we go to the next one. This is an important theorem called theorem of stability. Suppose that V is a finite dimensional vector space where E is an element that V, then alpha equivalent one predator A E is invertible. The finite dimensional vector space is if we have a linear map, a linear operator D on finite dimensional vector space V, the objectivity, surjectivity, and uh, objectivity lie the same. So let's consider this A lies A that is this is by definition injective and surjective. Suppose now we want to show that uh, B moves, and then we will we will show D is also surjective. object, then then kernel space is just the zero vector, containing the zero vector, and then from fundamental theorem, the dimension of the null space is equal to the dimension of the vector space minus the dimension of the range D. So the dimension of the null space is already zero. So that means this is zero. Let me rephrase. Suppose D is subjective. D is objective. Then for range D is equal to this implies the this one here is this N, any letter. But what the idea is that dimension is equal to the ratio for the dimension cancels out. If the dimension is just zero, this means just consists of the zero vector. It's E is uh, skipping some things. I skip the line. Suppose T is injective. You get ahead of the place. Begin from the beginning, my notes is C suppose T is subjective. Then our what? No, suppose T is subjective first. We want to show injectivity implies subjectivity. Suppose T is injective, thus your null space T is just zero vector. And by fundamental theorem, we have the dimension of range is equal to the dimension minus vector space D minus the dimension of null space D. And no, this is just zero. This means it's just the dimension of D. And hence, as the range of D is equal to vector D. So, for second, subjective to the is subjective. Now for C, for D, nice. Want to show that D is equal to show that D is injective. We want to show D is subjective. The suppose we have subjective. Then range of P is equal to vector space. Then the dimension of null space of P is equal to the dimension of minus the dimension of the range. Since they are equal, it gives us 0. Thus, we get null is equal to 0. This means, therefore, P is strict. So we are okay with the injective. Now we want to show that P is also surjective. But we have already assumed that the earth is surjective, so we get since P is surjective, the assumption and injective is invertible. It for our linear operators. Now, let me spend the rest of the minutes by stating what we will do next. Now, next meeting, next recording will focus quickly on we will focus quickly on uh, quotient products of vector spaces, and then we will also go quotients. Let me have this remark here that we will go these topics quickly and leave much for reading. For the reason of much of these topics will not be used in the succeeding lectures or the lectures that will follow after this this. We'll go quickly by stating results and explaining what they are, not gonna prove them. Maybe we will spend the meeting on brushing up these results, product spaces. This is familiar. And then quotients of vector spaces. We can think of this as cosets, and then we will also have the first isomorphism theorem, the dimension or the isomorphism between the quotient space, the vector space, modular kernel is just equal isomorphic the image or linear P is just recall or just have some restructuring of main results from isomorphism theorems, groups and rings, or fields or any structures. We have a name for that. See, sometimes we call that the universal mapping property, just the universal property. And then the next part is this is part one. Part two, we will start with the concept of spaces. What space, of course, it's an important concept in linear algebra. It's always can always see this in analysis, in analysis, functional analysis, higher courses of analysis. And I think this ends the lecture today. Let me end the recording.